Hello friends, welcome to all. Myself Vishal Jogidas. Today we will discuss about Pitot Tube and Rotameter for flow measurement. And this topic is covered in the subject of industrial instrumentation. We have already studied orifice, plate and venturi tube for flow measurement. Now we are going to discuss Pitot tube and then we will discuss about rotameter construction and operation. So let us start with Pitot tube. It is invented by Henry Pitot in 1732 to measure the fluid velocity. So this tube is used for measurement of velocity of fluid. It is used in wide range of flow measurement and applications such as air speed in racing car, then air force in fighter jets. So in this type of applications we are using this pitot tube. This is the typical pitot tube. Here we can see this one is the pitot tube, okay, and it is placed inside the flow. The orange color pipe is flow of fluid and direction of flow is given by this arrow. So whenever the direction of flow is in this direction, at that time the pressure is created in the pitot tube. So flow is directly converted into pressure. So this way we will measure flow. Principle: it consists of a cylindrical probe is inserted in the fluid stream. In this device, the velocity head is converted into an impact pressure that we have seen in a figure. It means whenever the velocity is this, it is directly converted into impact pressure of this tube. The difference between the impact pressure and static, the pressure is a measure of flow rate. So difference between this impact pressure and static pressure is the measurement of flow rate. So this way we can measure flow rate. Now a blunt object is placed in a fluid stream. So obstruction to the flow as shown in figure. Here we can see this is the object, and due to this object there is a change in pressure and velocity. Here we can see the pressure is before this object, we can see the pressure is P1 and velocity is V1, and at the blunt object pressure will be P2 and velocity will be 0. Why 0? Because at this point, at center point, there is a velocity is 0. So this is the effect of blunt object on flow stream. As the fluid approaches the object, the velocity will decrease until it reaches 0 at the point where it impinges on it. It means whenever the fluid is approaches to the object, velocity is decreases and it will become 0 at the point where it is impinges on it. So we have seen this point where the velocity is 0. This results in increase in the pressure on downstream side. So what will be the result? Due to this object, there is a increase in pressure in the downstream side, and this is the mathematical expression: P1 upon rho 1 plus V1 square upon 2G is equal to P2 upon rho 2 plus V2 square upon 2G. At the point of impact, V2 is 0. We know that. In other words, the kinetic energy has been converted into potential energy. See, V2 velocity 0, it means kinetic energy is converted into potential energy, and the result is reflected in the value of P2 at the impact point. P2 will be increased. Where V1 is the velocity of the fluid on the upstream, V2 is equal to velocity of the fluid on the downstream. Rho 1 is equal to density of the fluid on the upstream, and rho 2 is the density of the fluid on the downstream. So what is upstream and downstream? So before this blunt object, this is known as upstream and this is known as downstream. Okay. This new pressure, known as the total pressure, comprises the normal static pressure and pressure produced as a result of energy conversion when V2 is equal to 0. For incompressible fluids, rho 1 is equal to rho 2 is equal to rho. So the equation we have seen before will becomes P1 upon rho plus V2 square upon 2G is equal to P2 upon rho, because rho 1 is equal to rho 2 is equal to rho. So here is rho and here is also rho. Now why we have neglected V2 square upon 2G? So here is the answer. We know that the V2 is equal to 0. So by putting this value, this term will be vanished from the equation. V1 is equal to 2G under V1 is equal to under root 2G P2 minus P1 upon rho. So this is the formula for velocity V1 or velocity 1. G and rho are constant for particular fluid. It means these two are the constants. It is not to vary with time. The pressure difference is proportional to the velocity of fluid. So this pressure difference P2 minus P1 is directly proportional to the velocity V1, because this rho and G both are constant. So P2 minus P1 is directly proportional to velocity V1. This is S-type Pitot tube. Here we can see this one is the Pitot tube, okay, and duct for stack is here, and gas flow will be from here. Here is a point 1, here is a point 2. So this is the S-type Pitot tube, and velocity of the pressure will be measured using manometer. So manometer is nothing but a pressure measurement device. So this level is known for pressure. So whenever there is a gas flow, at that time this liquid level inside this tube is changes, and by measuring this level using manometer, we are actually measuring the flow of gas. Pitot tube with manometer. So this is also one arrangement of Pitot tube with manometer. Here we can see this Pitot tube, and one end is placed inside the pipeline. So this is the another arrangement for pitot tube. This is also one arrangement for pitot tube. Here also there is a low pressure tape, then high pressure tape, and this one is the pitot tube, and flow impact opening is here. So basically we have to just create the convert the flow of a fluid into the pressure. Now operation of pitot tube. When the blunt object is replaced with a tube having a small opening facing the direction of the fluid flow connected to a differential pressure gauge as shown in figure B. So if we are placed in place of a blunt object, if we place the tube with a small opening, then and its face is should be in the direction of a flow. So it is connected to a differential pressure gauge. As there is no flow through the tube and since the flow is brought to rest, the new pressure developed and sensed is impact pressure P2. So due to this object, one new pressure is developed and this pressure is known as impact pressure P2. A static pressure reading P1 is taken upstream a little away from the tube. By measuring the differential pressure, the velocity can be computed by knowing the density of the fluid. It is very convenient to measure the static pressure in the close neighborhood of the tube. So it is very convenient to measure the static pressure in the close neighborhood of the tube. Okay. So this way we can measure the flow. Now what are the advantages by measuring this method? So it is very simple and low cost device. Another advantage is it does not produce appreciable pressure loss. It can be easily inserted through a small hole in the pipe. So there is a simple arrangement and it is very useful for checking the mean velocities of the flow in venturi nozzle or orifice plate. So in all these devices we can use this pitot tube. Now disadvantages. It is not suitable for measuring low velocities or below 5 meter per second. So for low velocities it is not suitable. It is a disadvantage or limitation. It is sensitive to misalignment of probe with respect to free stream velocity. So if the alignment is not proper, then it is sensitive and it may causes error in the measurement. So this is also disadvantage. It is not suitable for the measurement of highly fluctuating velocities, for example highly turbulent flows. So it is not suitable for the measurement of fluctuating velocities. So it is also disadvantage. Now industrial applications. It is used to measure air flow in pipe ducts and stacks. And it is also used to measure velocity of liquid flow in pipes and open channels. So these are the typical applications. Now we will discuss about another instrument for measurement of flow, and it is a rotameter. So rotameter is a very important question regarding exam point of view. It consists of a vertical tube with a tapered cone in which float assumes a vertical position corresponding to each flow rate through the tube. It is also called as constant pressure drop variable area meter. So this type of meter is also known as constant pressure drop and variable area meter. This is the typical diagram of a rotameter. So here we can see there is a cone type of arrangement and it is placed vertical. Okay, and in the center we can see float, and it is a tapered metering tube. Okay, and flow is flowing from this side. So whenever there is a changes in flow rate, at that time this float will position of float will be changed if it is upside or downside. So it is changed and it is measured with this measure tape. So this is the way or operation for this rotameter. A rotameter is a device that measures the flow rate of liquid or gas in a closed tube. So this tube should be closed. Now we will discuss about operation. It is a vertical tube of conical shape, the area gradually expanding from bottom to top. So here we can see that the area of here is very small and it is gradually increases, and at top it is maximum. So this is the special arrangement. The fluid allowed to flow in an upward direction in the tube. Okay, fluid is allowed to flow in an upward direction in the tube. Here we can see that from here the fluid is allowed in the upward direction. If a disc is placed which is free to move in the fluid path, it acts as a float in the fluid. So this disc is nothing but float. So it is free to move in the fluid path and it acts as a float in the fluid that we have seen in a figure. An orifice is set up between the perimeter of the disc and inside surface of the tube with a corresponding pressure drop. So orifice is set up between perimeter of disc and inside surface of the tube. Initially, when there is no fluid flows through the rotameter, then float is at equilibrium in a vertical tube. So here we can see this one is the equilibrium state. Okay, whenever the no fluid is flowing from this, at that time the float will be at equilibrium position. When fluid flows through the rotameter, it will affect the pressure drop, altering the relation between the inlet and outlet pressure. So whenever the fluid is flows, what will happen? It will affect the pressure drop and altering the relation between the inlet and outlet pressure. Okay. Thus, upsetting the equilibrium for force acting on the disc. So this is the setting of equilibrium for force. It is acting on the disc or float. The disc will then move up or down the tube by creating variable area of the orifice until the pressure drop is at original value when the forces are again at equilibrium. So equilibrium position is well defined. So whenever the measurement is done, after that it will be reach at original position, or it is known as equilibrium position. The position of the float in the tube is then measure of rate of flow. So the position of the float in the tube is then measure of rate of flow. Okay, so flow rate is directly measured by the position of float. Now analysis of rotameter. Consider the forces acting on the float in the vertical column of liquid as shown in figure 2. Okay, so we will consider the force acting on the float in the vertical column. Okay, the effective weight W acting on the float is given by W is equal to Vf into rho 2 minus rho 1. Vf is the volume of the float, rho 2 is the material density of the float, rho 1 is the density of the liquid. So this is the equation by which we can measure effective weight. So this is the way, and we can see different dimensions in this figure. This is zero position, then force, this is the diameter. So these are the dimensions of this rotameter. This is also the one arrangement of rotameter. Here is flow is from here to here. This is the float, and it will flow from here to this direction. Force Fd acting in downward direction on the upper surface of the float. So this force is given by Fd is equal to rho 2 into Af, where rho 2 is equal to pressure per unit area on the upper surface of the float, and Af is the surface area of float 1. Okay, so this Fd is acting on the downward direction, and another force Fv is acting in the upward direction on the lower surface of the float. So Fv is equal to P1 into Af. P1 is the pressure per unit area on the lower surface of the float, and Af is equal to surface area of the float. So this is the equations of two forces acting upward and above and below the float. These two forces are acting above and below the float. Now advantages of rotameter. It gives direct visual indication on a linear scale. Okay, its cost is low, it has a high accuracy, then a rotameter requires no external power or fuel. It uses only the inherent properties of the fluid along with gravity to measure flow rate. So it uses inherent properties of fluid along with gravity, A rotameter is also a relatively simple device. It can be mass manufactured out of cheap materials, allowing for its widespread use. So we can manufacture in a mass for cheap materials, so it allowing for its widespread use. So these are the advantages. Now limitation. Due to its use of gravity, a rotameter must always be vertically or oriented and right way up with the fluid flowing upward. If the position is changed or inclined, then it cannot work properly. Disadvantages. Graduations on a given rotameter will only be accurate for a given substance at a given temperature. Rotameters normally require the use of glass or other transparent material. Otherwise, the user cannot see the float, and this limits their use in many industries to being fluids such as water. So, this is the disadvantage. We have to use transparent material compulsory, otherwise, we cannot see the float. Rotameters are not easily adapted for reading by machine. We can visually measure in a rotameter, but it is not adapted by machine. Applications of rotameter. So some applications are in laboratory, then testing in production lines. It can be easily integrated for instrumentation with alarms, indicators, controllers and recorders. So these are the typical applications. Thank you.